Welcome back. This is the continuation of this strong induction lecture that's doing some applications to number theory. And I've kept the template up. This was the same as it was before with this little adjustment that we'll see in a second why I did that. Now I want to talk about integer division with remainder. This is something that you've all done at some point, elementary school or whatever, at the level of a calculation. So let's just do an example here to indicate what I mean. What is 150 divided by 7? And I don't want just the fraction, 150 over 7, the rational number. I want this so-called integer division. So you do long division. I don't know if they still present it this way in grade school these days, but the way I learned it was you make some sort of array like this, and I say 7. Okay, so 7 divides, how many times can I put 7 into 15? I say 2. 2 times 7 is 14. So then I do that, and I subtract, and bring this down, get 10. How many times can 7 go into 10? Answer 1. And so I put 7 there, and I get 3. And now 3 is smaller than 7, so we end. And so we have the answer. So 150 different ways of saying it. 150 divided by 7 is the quotient 21, which is right here. That's an integer, by the way. And down here we have the remainder, which in this case is 3. And so you could, one way of thinking about what we did is we've written this improper fraction as an integer plus something less than, a fraction less than 1. And there it is. So there's an example of division. Now, it'll turn out, for what we're going to do, especially in number theory, we don't want fractions. We don't want to leave the integers, even though these are rational numbers. And how could we do that? So another way of presenting this same calculation, if you think of this is a true statement about numbers. If you multiply both sides by 7, another way of saying it is that 150 is some integer multiple of 7, 21 copies of 7 in this case, plus 3, which is the remainder. And let's see if I remember all the terms. So the quotient again, 7 could be called the divisor, the thing you're dividing by. I think this is called the dividend. I mean, not commit to that completely. This is the remainder. Main terms we need are quotient and remainder. All right? And what I want to prove, the theorem, is that you can always do this for integers. As long as you're not dividing by 0, there's always a way to write any given number as a quotient times the number you're dividing by, plus a remainder that is small in some sense. And this is actually some sort of an algorithm that gets it for you. So this is often called the division algorithm. But the theorem I'm proving doesn't really have an algorithm, certainly not this one. So I'll just call it the division theorem. Division theorem, integer division theorem if you want. So how do I state this carefully for every, in general? Okay, and there's lots of versions. For this, I'm not going to do the most general version at this time. First, I just want to concentrate on things where all the integers we're looking at are greater than or equal to 0, okay, because that's the best setup for induction. Later, we'll talk about how it generalizes. So let's say it like this. For all integers, a greater than or equal to 0, and b strictly greater than 0, there exist unique integers q and r, q for quotient, r for remainder, such that a equals b times q plus r, first of all. And second of all, the remainder has to be small. What does that mean? It means that 0 is less than or equal to r is strictly less than b, the thing you divide by. In our example, a was 150, b was 7, so we had to keep going until the r, we had some partial remainders along the way, but eventually we had to get down to r equals 3, which was less than 7. So this is the critical condition, two conditions that we need. And I put unique in parentheses just because that's the part of what I'm proving that's going to be delayed until later. So, well, maybe I'll get to it this time, but uniqueness, maybe not, may be proved later if I run out of time. But it's very crucial. It's the fact that there's only one quotient and remainder pair that have both of these properties. It's not like there's, you know, I divide to get one answer and you divide to get another answer. No, there's only one answer for a given A and B. There's one QR pair that has both these properties. That's what uniqueness means. Okay, but the first part that I will do right now is the existence proof. And that's the part of the proof that's going to use strong induction. So proof. And this is a slightly harder one than others we've done because there's so many variables floating around. And so you might worry about, well, which one? Like, what's in? Okay, and there's maybe no way to know in advance, but I'm going to say that for this particular proof, using induction on A, strong induction on A, is the thing we want to do. And then we'll see how B and Q and R, those are all going to be quantified variables and things. But A is the induction variable, which has been always called N up till now. But you can call it whatever you want, right? So here we go. Fix arbitrary integer A greater than or equal to 0. Okay. And then right away we have to make some assumption. Okay. Assume for all integers m in the range starting at 0. This particular that's what was calling b before 0 is the smallest value of the induction variable, and ending just before a blank. All right, let's leave this blank for a second because I'm supposed to copy this statement down, but I haven't completely symbolized it yet. So I'll fill that in a second. What are we proving? We're proving this very statement, just the existence part. This is proof of existence only at this time. We'll do uniqueness separately. Okay, so existence. But let's say more carefully the rest of it. Okay. I guess there's no harm. I could have fixed B. Let's fix B up here as well. Positive integer B, because that's not going to be changing on us. All right. But what I'm proving is an existence statement. There exists Q in Z. There exists R in Z. A equals BQ plus R. And 0 is less than or equal to R is less than B. All right, so that's just this with quantifiers in there. So we're assuming, going back to the assumption, that's the same thing we were assuming about M, okay? But you have to be careful because the Q and the R we're about to come up with, the quotient and the remainder for A, are very likely not the ones that are going to work for M. So I'll write this statement down again as our assumption, but I'm going to carefully use new letters. Let's use Q1 and R1. And there's still quotient and remainder, so I still want to keep the Q and the R, but the subscript is going to make it different. And it's M instead of A. So M equals BQ1 plus R1. And 0 is less than or equal to 1 is less than b. So that's the quotient and the remainder that work for m. They depend on m. Okay? And we haven't selected an m yet. We've just made this assumption. Later in the proof, we'll pick a good m that helps us for a. All right? Now, so we've done the setup. And you see that the setup can become complicated if the statement to be proved is complicated. But we just followed these steps, and we're here now. Proof P of n. Often need base cases. So the next thing to think about is, well, what are the base cases? Are there any sort of low values of a where it's easy? Which might have to also be separate anyway. And if you think about division and you do some more divisions, like we did 150 divided by 7, if I had done 8 divided by 7, that would have been shorter. That would have been quotient 1, remainder 1. 7 divided by 7 would have been quotient 1, remainder 0. But if you think about it, the very simplest thing I could have done is something like 5 divided by 7. What's that? Well, it's too small, right? So I can't fit any copies of 7, and 0 copies, and I'm just already at the remainder with a quotient of 0 and a remainder of 5. And that happened because 5 was small. It was already less than 7. So 6, 5, 4, 0 through 6, all this would have happened. We would have gotten a 0 quotient, and the remainder would have just been the same number a, this is like a here, that we started with. So that's actually the base case. There's a whole bunch of base cases at the beginning for the values of a that are already less than b. And so this is one of the hard lines in the proof, thinking of making that classification. We know by algebra or whatever that either a is less than b or a is greater than or equal to b. The trichotomy law for integers or real numbers, whatever. One of those holds. Okay, that's a known or statement, so we're going to use cases. Even though the template doesn't tell you in advance what the cases are going to be, that's one of the things that makes it harder. But anyway, so case 1, what are we going to do if a is less than b? Assume that. And prove, let's call this G for goal, statement G. All right, and we'll do what I said over here, but we have to do it in generality using all these symbols. So we're proving an existence statement, a double existence statement, where these things have to be true. But this little calculation over here is trying to tell us what we should be doing. Okay, so the idea is, because a is already less than b, we don't really have a division happening, but I still have to choose q and r. Let's choose q to be 0, and choose r is equal to a. All right, and remember, going back to other points of logic we were doing recently, since a is already a fixed constant, as b is, the thing I pick is allowed to have an a in it, or a b for that matter. Or it could be an actual constant, like 0, which happened over there, as long as it works. Now, what does work mean? Well, are these integers? Yes. A is an integer. 0 is an integer. So make that observation. Does this equation hold for the choice we just made? Little chain proof here. BQ plus R. Q was 0. R was A. So we do get A for the choice I just made. BQ plus R does equal A. And let's see. So what about this? Does the R inequality hold? Well, 0 is less than or equal to R. What was R? R was A. Because A is greater than or equal to 0. Again, negative integers, we'll worry about that later. A is not allowed to be negative right now. And let's see, and R is less than B because that's the case that we're in. That's the whole reason we made this case, because that would make the remainder just be equal to A. But this is the case where that works. Okay. All right, and that's the base case, which is actually B different values of A, 0, 1, 2, up through B minus 1, all fall into this case 1. All right, case 2. Assume A is greater than or equal to B. And prove the goal. Okay, so this is harder, all right? Because, well, what are we going to do? So we have to, of course, we haven't even used this assumption yet. Let's call this H for induction hypothesis. And how is that an assumption going to help us? And the way, let's do a little example to try to get ready for what the proof's going to do is 150 divided by 7. I gave you the fancy way to do it using this long division algorithm that produces 20 right away. But there's a much simpler thing you could have done when you first started dividing. Maybe they told you multiplication is repeated addition and like division is like repeated subtraction. Still dividing by 7. So the idea would be, well, maybe you could divide by 7. Subtract 7 over and over and over and over and over again until you hit the remainder. Of course, that's going to take a while, right? Dot, dot, dot. Okay. Division is repeated subtract. That takes a long time if you have a big number, so that's not how you divide in reality with an algorithm, but actually this will be the key to the proof. Okay. Because in the proof, you don't actually have to subtract all the way down. You only have to do one of them. This is the sort of amazing thing. After subtracting 7, you have a new number, 143, that has to have a quotient and a remainder, but that's less than the number you started with. So like if A was 150 and M was 143, the induction hypothesis solves 143 like by magic. You don't have to worry about the details of how that happened. The hypothesis just gives it to you. And I guess in this case, the quotient, called Q1, is 20, and the remainder is 3 for this guy. And maybe that happened by some long recursive process. But however it happened, that result is available to this proof when you're worrying about 150. Okay, well, if I just tell you that's the answer for this one, and then say with no further work, what's the answer for this one? Just a moment, I have to pause this. Okay, sorry for that interruption. That was something important that had to be done. I think I was right here. So we were saying that if you magically solved the 143, you have the quotient and the remainder for that, and now I'm asking you to get 150. Well, look, I just added one more 7 to this. So that means the quotient here should be 21, and the remainder is still 3, matching what we did before. Okay, but the great thing is that works in general, so that's just what this proof is going to do, but it maybe looks harder because of everything has to be in the symbol. Okay, but the key insight, so here's A and B, right? A was 150, B was 7 in this example. Well, what we did was we subtracted one copy of B from A. And that led us to M, the M we want to use here. Okay, so that's what we have to do. So let M be A minus B. Those are constants. We can choose whatever we want for M. If it's in the range, first of all, is it an integer? Yes. Because it's a difference of two integers, A and B. It's got to be an integer. So that's one thing. Is it greater than or equal to 0, which it needs to be? Yes. Why? Because in this case, A is greater than or equal to B. So M, namely A minus B, is greater than or equal to 0. And this wouldn't have worked in case 1. So case 1 had to be separate for this reason here. So repeated subtraction, you don't want to do that if you're already less than 7 or whatever. And finally, is m less than a? Strictly less than a. It is. Why? Because b, unlike a, which could be 0 in general, b is strictly greater than 0. So if you subtract something strictly greater than 0 from a, we're less than a. Okay. And so we've now checked. So you can't just use the hypothesis blindly. You have to check. Is the universe right? Integer, 0 less than or equal to m less than a. All of that works for the m I'm choosing right here. But we had to check it. The proof has to check that. Okay. But that means, so we may apply induction hypothesis H to m. Hope it's still, yeah, it looks like it's still recording. Okay. Okay. What does that get us? It basically gets us the solution for 143. This is the sort of magic of induction. You don't have to keep subtracting again and again and again, although algorithmically that might be what ultimately happens if you were going to do it in full. The proof, however, gets to assume that the smaller instances are already solved. So we know an existence statement with no further work. There exists a Q1 integer, there exists an R1 integer, where m, namely the m I picked, a minus b, is bq1 plus R1, and the remainder for m is small in the required sense. 0 less than or equal to R1 is less than b. Okay. Now, we still have to do the goal in case 2. We have to choose Q, we have to choose R to satisfy this and that. But now we're almost there. So remember when we went from 143 to 150, we added 1 copy of 7 back, so that's now we're going to do that here. Add b to both sides, and we get that a itself is b plus bq1 plus R1, and I can absorb the b, I can factor. So that's b times 1 plus q1 plus R1. That's something I know now from the induction hypothesis. Well, now, comparing to what I need here, right, I get to pick Q and R as the proof writer. I can choose an example that depends on previous constants. And now it should be evident from here, what do I have to choose? The final quotient, the one for A, is going to be 1 plus Q1. And the remainder for A, R, is going to be R1. So notice that all the things. So Q and R are in Z, since Q1 and R1 are in Z. Adding 1, of course, closed under addition, all that stuff. Also note, by the very calculation we've already done, A equals BQ plus R. That is true. That's the whole reason we did all this. And what else do we need to prove? We have to have this. 0 is less than or equal to R is less than B, but because R is equal to R1, we already know that about R1, so it's still true for R, which is equal to R1. And so suddenly we're done. The induction is a little sneaky. It seems like why don't you just subtract a whole bunch of times? Well, secretly that would happen here if you were going to solve it in full, but the structure of the proof lets you just recursively solve it. You know there's a solution, and then you just have to do that last step to get back up to A. Okay, so that is the end of the existence proof for the division theorem. Again, I don't want to, we'll have a separate segment where I talk more about uniqueness and other types of things like whether you can do it for negative integers, but not yet. One little comment I will make before stopping this segment is that why was it strong induction as opposed to ordinary induction? And the key realization was this idea that the quotient and remainder for a minus b are very closely related to the quotient and remainder for a and b. Whereas if you just went to a minus 1 for an ordinary induction, it's not. Actually, that does work. In fact, there might be a homework problem where I ask you to prove this theorem again with ordinary induction instead of strong induction. It does work. The details look slightly different, quite different actually, but it does work. Okay. On the other hand, the theorem from the previous segment, the existence of prime factorizations of integers, that totally does not work as an ordinary induction proof. Like, for example, if I tell you, okay, I've already factored 100 into primes, how does that help you factor 101? There's no relation between those two factorizations. In general, the factorization of n and the factorization of n plus 1. So that's the one where you really, really need it. But there are definitely cases like this theorem where either method might conceivably work. The strong induction, I feel, is perhaps more appealing. It makes contact with repeated subtraction and so forth. But there you go. So there's another example of a strong induction proof. And I'll say a little bit more about integer division in the next video. See you later.